Okay, here is my previous code in OpenGL. And if I start it, this is what we did last time. There is no collision, but we can move the paddle around. And we will delete all of this and start fresh. We will start fresh by making everything in one file. To the top right, we have this the speedrunners use. We can even start it right now. And now we are at the stage of rendering a triangle. And we will try to reach adding a win condition. Like we're making the snake game. The snake game where you're a snake that has to eat the little dot. Snake game. There should be, yeah, everybody knows the snake game. Like we'll make something like this. I have used to learn this resource, learn OpenGL. And this is the best resource on OpenGL. Went through getting started. And let's do this. Let me start the server for the horizontal chat below. And yeah, it seems like the horizontal chat will get only from Twitch messages, but I'll check them. I'll look at them at another window. Not that big of an issue. And let's do this. I've previously made the previous game. I've made it in plain English, but we'll be changing that. We'll be coding like everybody else, not in plain English. It's time I switch from plain English to coding. With plain English, what I achieved was that I was able to focus just on the OpenGL concepts. The problem is that I haven't learned the syntax or how exactly, for example, to create a VBO or VO or EBO. All of these objects, how to exactly create them. I haven't learned that, but I know the logic behind everything. So we should be fine as long as I am able to use as reference. Like here I've gathered for creating a window all the functions we need. So we'll just take whatever we need. And here we will start from scratch. Yeah, so processing input. Let's delete these vertices. And in main, why not start from scratch? From absolutely scratch. Okay, now if we run it, what will happen? Nothing. There has to be a main function as a starter. Now will it run? Yeah, but the console, where's the console? Oh yeah, it closed instantly because For it not to close instantly, we need a while true loop. We need a loop that is constantly running. Which is the actual game loop. So for creating the window, let's see, yeah. Here I have reference of what to use. So we initialize the glfw window. Oh, we are for creating windows, like for making a game from scratch, we use OpenGL and C++, but OpenGL doesn't handle window creation, like having a window, processing input. All of that is through glfw. And another option is SDL, which is the more popular option. SDL is used in a lot of popular games. But we use glfw because, for starters, this tutorial uses glfw, and also it's easier to set up, and we don't need for now SDL, but we will transition to SDL at some point. So for creating a window, these are just standard things where we have to initialize a bunch of things, which is calling functions that somebody else has made. Do I have the includes? No, I don't have them. Let's go in here inside rules. Yeah, here are all the includes. So we need for read and write. Let's leave it out without read and write for now. We'll use it when we need it. What we need is glfw. We need to include OpenGL. And look at how when we included it, the functions, we can now use them because they are from glfw. Now we include glat, which is OpenGL. What else? Okay, those are it. Let's see what we get if we start it. Nothing, because we still don't have the main render loop. But before that, we even need to check more things. We need main loop. Yeah, this is starting point, creating window. This is just code that we write once and we never write again, and like we don't have it remembered on top of our head. Okay, this creates the actual window, and here are the dimensions, the width and height, and the title. We'll call it Snake Game in single file. By single file, what this challenge means is that we will not be creating a separate header file for shaders. We'll be just working in this file. Maybe we can create classes inside this file to make it easier, at least a shader class. But we'll see. So this should create window. What else do we need? Initialization for OpenGL. And this function is to tell OpenGL in what part of the screen are we rendering, because we can say, for example, to render just on the, you know what, when we start it, we'll change this and it will be obvious instantly what it does. On every Windows resize, call. Okay, this function is for when the window resizes, we call this function which we have to create. Yeah, Visual Studio just auto-completed it. Hopefully it's the right one. But this is when okay, we will comment it out and it will, this is ways to show something is when we just run it. Resize. What else? Okay, this is the main render loop. This is the main render loop, and let's actually run it like this. Let's run it like this. And here's the main render loop, but we have to close it because we still need to just write some boilerplate text. Okay, here Visual Studio Code just suggested code here. Here, swap buffers. What this means is that there are always two buffers. One is the main one, what is currently on the screen shown, and the other is a hidden buffer, kind of like behind the scenes, where it's the buffer we actually draw on. When we finish drawing, the buffers swap. If we don't have this swap, we'll be working just on one buffer, and there will be some kind of stuttering, like think of it like we have on the window a picture that is our final product and all the people are looking at it, and behind the scenes we're drawing on another canvas, and when we're done drawing on another canvas, we switch them, the one on the window, and viewers now look at the new canvas. Whereas if we don't swap them, it's like we're drawing in front of them and they're looking at us drawing. If we don't have this, we will maybe see OpenGl drawing. Here, clear color, I think this will have a black background. And let's run it actually. Yeah, we have a black background. Let's change this to, for example, red. This is red, green, and blue. Maybe I should increase the font. Yeah, I can increase the font through, like I'm using Vmotions inside VS Code, and I think it's using my it's using the Control Plus. Fine, I'll leave it like this for now. Hopefully the font size is big enough. Let's make the background red just to play around with it. And here the background is red just through this line. And here we commented out this function where it's for callback when the size of the screen changes. And why do we need it? And when we start the game and we resize, look what happens. It's hard to show when we're not drawing anything. So we'll leave it like that. When we render a triangle, I'll show you. So let's leave it as black screen. What else do we need? After the while loop, we will terminate glfw, like to properly stop whatever glfw has initialized. And for processing input, I have here function from the past, but we're not calling it. We have this function for processing input that checks if the escape key is pressed, and if it's pressed, we close the window, but we're not calling it. Let's check process input. Okay, we can just call it regularly. Process input and window, and let's run it. And now when we start the game, we should be processing input. Now when we press escape, it should close, and it closed. Just because we're just calling this function, this process input function, and inside the function, we just check if the escape key is pressed. And if it's pressed, we tell glfw to close the window we've given as reference. Those are the basics. Our goal currently, that can be seen on the top right, is to render a triangle. And then to move, to have a movable rectangle, which is our player. This. By movable rectangle, okay, have to stand up. By movable rectangle, we mean this right here, the top of the snake. Like, I don't know which one here is the bottom or top. Let's say this is the head of the snake. So movable rectangle is just this one, to move this one. That will be the next goal. Then we spawn the snake foot, which is this red dot. We'll make it spawn. We'll make it spawn, and oh, come on, this microphone doesn't want to stay at one place. We'll make the food spawn, then we should be able to eat the food. Okay, I have fixed it. Then we should be able to eat the food, and let me move OBS from here and open the chat. And test if Twitch can be seen. Yeah, Twitch messages are seen. The camera is not centered. Yeah, okay. And we'll not go through all of these, like me explaining them. Let's just call them. So for rendering a triangle, we want, it's not that much code to render a triangle. I can even show you a little bit something that will make it more easier to understand how we will do this. Hello triangle. Yeah. So our goal to render a triangle is to send the shaders, the information for rendering a triangle. We have to send the coordinates for the 3 dots. This is how, and we tell OpenGl to render a triangle. That's really simplified because OpenGL, all the advanced graphics that you see everywhere, is just rendering triangles and combining those triangles. So if we want to render a rectangle, we have to render 2 triangles. I think they have it inside here, an image that shows it. Yeah, here they render a triangle, and we will render a triangle, but here, look on the right, how there are 2 triangles here. So if we want to render a rectangle, we need to render 2 triangles. Like OpenGL and all the other games, they work behind the scenes just with triangles. And a 3D model is just that couple of triangles and simple shapes that are combined together. And the only thing we can tell OpenGL is like these dots here, and OpenGL like does the actual drawing. And we tell OpenGL through the shaders. We have to send them to the vertex shader, and the vertex shader, all it does is changes the position if it has to. And then the other important part is the fragment shader that does all the coloring. But we'll focus just on the vertex shader. That's about it. Now, we're in the while loop, and currently we have a goal to render a triangle. Let's see inside rendering. I have in a rendering file helpful functions because I haven't remembered the syntax. Yeah, in drawing. I haven't remembered the syntax, but I know the logic behind them, which should be enough. Okay. Now we have our render loop. We have our render loop, which is this. And it runs while the window is active and it shouldn't close. We swap the 2 buffers that we talked about, and we clear the screen every time and replace it with a black screen. If we want, we can replace it with the red, green, blue. We can replace it with the blue color. And if we start, we have a blue color. We'll keep it as a black one. Yeah, all red, green, and blue, all zeros is just black color. Now, for rendering a triangle, we need some setup. The first and main thing is we need the vertices, which is just an array of float values. And it's a 1 direction array. It's not 2 directions. Drawing. Not indices, but we need vertices. In Windows, vertices. No, okay, let's check in the rules. Okay, where should we initialize it? We'll just do it in the main function. Here, for example. And here is our float array, which will be just vertices. And we need to put values there. So if For the values, we need to put coordinates. And for the coordinates, they are with the origin, like the center of the screen is the 0th position. So if we want to say here, like the top of the triangle, on the x-axis, it's still 0, but on the y-axis, it's 0.5. Like a 1, the values are from -1 to 1. Like, that's all we get. And in order to have, for example, values like the actual screen resolution, to not work just with between -1 and 1, we need to multiply all the vertices by a matrix. We need to multiply them by a orthogonal matrix, which is a bit more complicated stuff. And it will allow us, what that matrix will do, it will convert coordinates from the vertices that are from the screen. Instead of writing like from 0 to 1, we can write instead of from -1 to 1, we can write from 0 to the actual screen width by multiplying with a matrix. But I'm wondering which one we should pick. Okay, let's start with like this, the simplest one. We'll keep it as simple as possible and see how far we can go. So for the vertices, we need to write the coordinates of each of these dots, the 3 dots. So this one, it should be 0. It's on the x-axis. Let's start with the top one and just leave it as zeros. And here it's 0.5f. Then the next coordinate will be, let's say the bottom right. Okay, sit down. The bottom right will be just 0.5 to the right and negative 0.5 downwards on the y direction. So let's write them. Yeah. So bottom right, it's 0.5f and negative 0. I don't know how Visual Studio Code is auto-completing these vertices. That's really weird. And then bottom left is on the x-axis minus 0.5 and on the x-axis minus 0.5 and the y-axis minus 0.5, which Visual Studio Code is auto-completing. And we have the vertices. Next, we need to create VBO and VAO. I think they're vertex buffer object and vertex array object. They will make sense once we write them. Yeah, so in drawing we need a VO. Yeah, create array object. And the name of it, I think they're stored in unsigned int VO. And here we give the reference to the VO. So we in OpenGl, vertex buffer objects, vertex array objects are objects that we don't have stored, like for example when we initialize a class and we have the object. It's not like that. All we have is a reference to the object as an unsigned integer. That's all we have as reference to that object. This is very common in OpenGL. Like in OpenGL, we will be dealing a lot with unsigned integers to reference different things. So we create the vertex array object. What else? Yeah, let's bind it. And binding is when we bind it, we tell OpenGL this is what we're working on. Because afterwards we will have functions that use VO or VBO, and instead of giving it as a parameter, we're just binding it. I think the positive of doing it like that, instead of giving it as an argument to a function, is that probably we can bind it in one place and we can use it in an entirely different place just because it's bind, and we don't have to pass it around in order to give it to a function as an argument. This is my logic behind it. That's how OpenGL decides to work, and we'll work with it. So we bind the vertex array object. We'll go over what all of this means, but we have to write it before that. And here Visual Studio just autocompletes. But is it correct? Okay, here we create an unsigned integer for the vertex buffer object. Can't I increase increment font size? Font size? Yeah, here. Let's change the font size to 16. Okay, this should be better to be seen. Greetings. Happy Chinese New Year. I'm not educated on when exactly is the Chinese New Year, but if it's today, then happy Chinese New Year. Okay. Now we've made the font larger. We're still on rendering the triangle. We'll pick up the pace if we want to finish the entire game. So now we have the VBO, and here this function generates the VBO and stores it inside, and stores the reference inside this unsigned integer. And yeah, this creates the object. Yeah, okay. Let's check here. Create vertex array object. Okay, we created it. VBO. Unbind. Yeah, okay. So this created the VBO, and this binds it so that we can work with it. In order to work with it, we have to bind it. It's the same as passing it as an argument to a function later on, but okay, we've bound it. Now we need to tell it, we need to give it the vertices. We need to give the VBO the vertices, these here. And copy vertex data, okay, is this. So to GL buffer data size of, and here the array, which is vertices. And here we actually give the array. Oh, come on. We give the array, and here we tell it it's a static draw. I think there's dynamic. Yeah, there's dynamic draw, but we're using static because I think static is for when things don't move and will not have to be drawn multiple times. Okay, we've given the VBO the vertices. We'll go over what that means after we draw the triangle. And then we need to tell OpenGL how to interpret the data. Here the location is 0. The size location, here the location is 0. We'll go over what the location is. We'll also need to actually create the shaders, the vertex shader and the fragment shader, because there aren't any default implementations for them. Like there are other shaders as well. They're vertex shader, geometry shader, other shaders. And we don't need to implement them. They have default ones. But the vertex one and the fragment ones, they don't have default ones, and we have to write them as well. Right now we are still working with the VBO. And here, offset 0. Offset will be 0. Stride is 2. But how did we type it? I think it was size of float times 2. We'll see if that works. And the attribute size, let's say it's size of float. Here on the specifics, I'm not sure. Let's see my pass version. OpenGL. No, it was actually here in vertices, size of vertices. Okay, this. Okay, GL float. Here I'm saying size of a float, and that each value is size of a float, that we're working with floats. No, this is that we're working with floats, GL float, and this is for the size that it's 2, that we're working with. We're giving it just 2 numbers. Like each point is just 2 numbers. That's all we're giving it. Here, the 2, and this one, I think it should be correct. The stride, yes, size of float, void, okay. We'll go over this, but what this is that all we're, because we're giving OpenGL just an array of floats, and it doesn't know how to interpret it, because it's just this number, another number, one more number. It means nothing to OpenGL. And what we're saying to it is that group them by 2. So these 2, then these 2, then these 2. That they're floats, and that the size of them, like they're 2, but what's the size? It's 2 floats. So just once again, all we're telling it is start from the 0th position and go through just 2 at a time. When we, and here, we gave it these vertices. And we gave the data by creating this array and telling OpenGL interpret the array by just taking 2 at a time. It will make sense once we create the shader. Enable, okay. And to draw it, and we can unbind them. So we have to vertex array and 0. This unbinds the VO. And then we need to draw them. We need to bind the VO. Oh my god. And here it's a 0. Gel draw triangles. And here we're using the function to draw these primitives. And the primitive we're working with is a triangle. I'm not sure if there are other primitives, but that is what we're working with. And these, I think this is to say that to draw 3 vertices, but we'll check. Visual Studio Code how to complete it. So I have to check in drawing. Yeah. So draw triangles from VBO using X number of vertices starting from Y. Okay. That's it. Yeah. So now we still cannot draw it. If we run it, it will not work because we need shaders. Here it's drawing nothing because we need shaders. And for shaders, we can once again go through references. Once we have the shaders, we'll have the triangle. I'll give a bit of explanation and everything will make a lot more sense. It's just with OpenGl, there is a lot of initial setup. Next, now, yeah, we create vertex shader object. Okay, so for the vertex shader and for the fragment shader, we have to create objects. We'll create them before creating the triangle. So here, before all of this, shader, and here, oh, come on. And triangle. This is the code for the triangle. And this is the code for the shader. Now for the shader, we need to create our vertex shader. Vertex shader. Vertex shader. And we need the source code, which I think is an array of characters. But actually, yeah, let's just work like that. So here, do I have the previous shader here? No, I need a simple shader to work with as a default one. I think they had it here somewhere. Hello triangle. Need a simple shader. Yeah, vertex shader. Oh, come on. And this is our vertex shader source code. This one, yeah, gets a position. It will be a vector 2, not a vector 3. And here it will be just a 0 value. And here for the source code, for the vertex shader, we'll give it this vertex shader source. We've created the vertex shader object. We need to do the same for the fragment shader. Yeah, compilation and then checking for errors. Yeah, before creating the fragment shader, okay, we can compile it. Vertex shader, and we can check for compilation errors. These variables will be to store if there are any errors. And in order to put something in them, we need to check with these functions. These functions just check if the shader we put inside here, vertex shader, if it has compiled successfully. And if it doesn't compile successfully, it will output a message in the terminal. And here we'll say vertex shader compile error, and it will give the info log that is additional context on what's wrong, and it will get it through here, which is once again the vertex shader. And now we move to the fragment shader, which is quite similar. Quite similar step as before. We create the fragment shader. And we also need to get its source code of a really simple fragment shader. We need its source code, which I think they had here also fragment shader. I'm looking for a really simple fragment shader here. Okay, here, fragment, yeah, fragment shader. And here we paste fragment shader. This one just sets the color of each vertex to be like red is 100%, green is 50%, and blue is 20%. We'll leave it as just a red color. We'll just leave it as a red color. And here for a vertex shader, this for the shader name, we will say it as fragment shader. And here, once again, fragment shader, fragment shader. And here the source code, which is fragment shader source code. And like before, we need to compile it and check for errors of compilation. This part for checking for errors is quite helpful because when we make changes, to the each one of the shaders, it's really helpful when we make a mistake to see where the mistake is and what the mistake is. We've compiled the shaders, but we still need a shader program that links together the shaders. And when we communicate with the shaders, it will be through the shader program. So shader program, I think it should be, unsigned int. Shader program. We create the program and we have to link them. So first attach, then link. Okay, so first we attach them. Shader program. And here, look at how we have to give as an argument the shader program. And we're not binding it. When we before had to bind it, and we used functions here, like here we had vertex, we had a VBO, and we had to bind it with this function. And look at how when we work with the VBO, like inside here, we are not mentioning the VBO anywhere as an argument because we bound it. But for the shader program, we're not binding it, and to use functions with the shader program, we have to give it as an argument. Like that's the main difference between binding and not binding an object. Here we attach the the vertex shader, and we attach the fragment shader. And now we have to link them. We link them. This is shader program. And once again, we check for errors because there can be errors even when linking. Not this. So this checks shader program for linking, and shader program linking failed if there's an error. And yeah, I think, we can also delete the shader vertex, the compiled vertex shader, and the fragment shader, because they're in the shader program. We don't need them separately. Vertex shader and the fragment shader. Now we can use the actual shader, and let's see. Before we draw, we need to use the actual shader with this command. Shader program. Now let's see what happens when we run it. And here we have a triangle. Now I'll be right back. We'll have a quick break here. Be right back. Need to go to bathroom. I'll be right back, and we have the triangle. Okay, I'm back. I'm back. Let's open chat. Okay. We have the triangle, and let's move our speedrun to the next goal of movable rectangle. But before that, I can give a quick explanation. For this triangle, we told OpenGl each of the 3 points with the help of VBO. And here, look at how much code we had to write just to tell OpenGl to write one triangle. And in order to not have to write it again and again, we use a VO, a vertex array object. And by using a vertex array object, it remembers all of the configurations we've made for that particular triangle. And next time when we want to render it, we just bind the VO and we draw. And that's it. The vertex array object simplifies everything a lot. And in the future, when we have even more complex configurations, just having a vertex array object saves a lot of time. And that's the main purpose of a vertex array object. But for a vertex buffer object, its main purpose is to tell OpenGl how to first give OpenGl the vertice data, and the second goal for the vertex buffer object is to tell OpenGl how to interpret that data. Because later on, we can, for example, for each vertex, we can tell OpenGl to add a color. Because right now, the shader is giving the same color for each vertex. But in the future, we would want to change the colors because we're making the snake game. And one rectangle will be green and the other will be red. To have different colors, we need to store this information in the vertices. And the way we organize the information is something like we've came up with it. And OpenGl has no idea what our organization of information is, because this is the x-axis and this is on the y-axis. And we only need these two, each of a time, to send two. But how would OpenGl know? It knows through a vertex buffer object. We generate a vertex buffer object, we bind it, we give it the data, and we tell how to interpret that data. And here we say, let me check if there's audio. There's audio. And here, this 0 is the same 0 as it's a location. It's in the shader, this location 0. So we are targeting the vertex shader. This a position variable, we are storing the vertex data here. But we'll have another one for the color. And these shaders, you saw how without the shaders, nothing renders. So here, if we don't activate the shader, if we don't use the shader and we run it, here nothing renders. Like, in order to render something, you need shaders. Like, they're that important. And the two shaders we use are a vertex shader and a fragment shader. The vertex shader, all it does is outputs a position. So as an input, it receives a position, and it can receive other data as well, but mainly in the position of each vertex. And it outputs a position. The simplex vertex shader outputs the same position it gets. But if you want to get some crazy effects like a water, etc., you would make it more complex here. Or actually, we will add some things like we'll multiply by a transformation matrix for rotating, moving around objects. And then the next after the vertex shader is the fragment shader, that the only job of the fragment shader is to output a color. It outputs a color, and here every time it outputs the red color. And so here for each vertex it outputs the red color. But now let's make it so we can change the color through the vertex data. Here, let's add another field for the color, which will be RGB, I think. Yeah. So here for the color, let's make it a blue color. So red, then green, then blue, which would be 1. And now let's copy it and paste it here and paste it here. Now this is the color, and look at how we've changed the organization of the vertices, like it's different now, but OpenGl still interprets it in the old way, which is wrong. It will think of this as one vertex, this another vertex, this as another vertex, so we need to change it. Here we need the stride. I think this is the stride, which should be now 2, 3, 4, 5. Now the VBO will go through 5 at a time. 5 at a time. Where here, this is the position, which is this part, the position. But we need another one. We need for location 1, here and a size of 3, the same stride, and starting position, size of float times 3. No, times 2. And now what we've done is we're telling the vertex object is to go 5 at a time. And for each one, to break it down, where the first 2 are the position and the second 3 are for the color for location 1. But we need to go inside the vertex shader and create the new position. Here we tell it location 1, and it's a vector 3, and here it's a color. But this is the vertex shader. We need it in the fragment shader. So we need to create another variable that instead of an in, it's an out, because we will by saying it as out, this means we're sending it to the next shader, and this will be just color. And here we we need to set it, so this new one, color equals a color. Oh, but it needs to be like this. So color equals a color. Yeah. So what we did is we are getting the color from the vertices float array, and we are storing it. We are storing it in the output variable. So we're doing that just so we can use it in the fragment shader, which here I have to have the same variable with the same name, same type, just instead of out, here it should be in. And in the output color, we should just say here color, and it will use the red, green, the three values of it. This is the fourth value is the alpha. Now, I think this is enough. And this should change the color to blue. This should change the color to blue. Yeah, it's blue, but not only that, we can change it. Now each individual vertex can have different color. So this one can be red. This one can be green. And the last one can be blue. And now when we run it, look at look at all the colors we get. Now, all we did was we told this vertex should be color red, this one should be color green, and this one should be color blue. And how did we get all the other colors? Well, we got them because the triangle is much more than just 3 points. I think it has 50,000 points it has to pick a color for. And as we haven't set it, as we haven't decided what it should be, OpenGl has to decide on its own. And its default implementation is to pick color between the vertices. So this is red, this is green, and here it should be 50% red, 50% green, and just combines them, and that's it. Now let's render a rectangle. Let's render a rectangle, which should be two triangles. It should be two triangles, and I think in the guide there are coordinates for doing a rectangle. I'll use the coordinates they've given because it's easier to show. Yeah, here. It's just easier to demonstrate. But where did they put them? Yeah, this. These are the vertices. But we need to... our vertices are just differently created. Here, so top right, okay. This is top right. This is bottom right. This is... yeah, but they're doing it differently. They're using an EBO, where you don't have to repeat vertices. Okay. But these are the actual coordinates. Okay, top right. So this is upward. Okay. We need... yeah, they're using indices, but we don't need that. For just a rectangle, it's okay if we repeat vertices. We don't need to go into EBOs. This will just complicate things. I want viewers to have an understanding of what's happening. So bind buffer, no. Yeah, okay. So we need here to start top right. Top right. So first this triangle. We can start from top left, top right, bottom right. So top left, top right and bottom right. Okay, so let's leave it as color blue for each vertex. And here we start with top right. No, we need to start with top left, which is negative 0.5 and 0.5. So this is to the left on the x-axis, and this is to the upwards on the y-axis. And so here it should be again upward, but to the right. And bottom left, bottom right should be here negative, and here should be positive. Bottom right. And now we want, and now for the other triangle, we want, we will start from, we can do it once more with top left, then bottom right, then bottom left. So top left, so top is here positive, here negative. Top left, then bottom right, here should be negative, and here should be positive, and bottom left, here should be negative, and here negative. And we don't need these vertices. But now, if we, let's see what happens if we play now. Look, it drew only one of the triangles. We need the other one as well, which we can get from here. When we draw triangles, we will draw actually 6 vertices. We will draw 6 vertices. Here we have a rectangle, and look at what happens if we change this 0 to 3. It drew the bottom one. Look at how we can pick which one it should draw. But we will start from the first vertex. And here we have a rectangle. We have a rectangle. Just one rectangle. And we need to... Oh man, this is so much code for something so simple. Oh my god. We need to... Yeah, let's make it the color green. Let's now transform it, which we will move into transformation matrices. I hope the audio is loud enough. We will move into... yeah, it's loud enough. It's just that my voice is without any emotion. Okay. Let's... Now we have a rectangle, and let's make it the green color. Let's make it the green color. Here. Make it the green color. So to make it the green color, in our vertices, we need to, our color values, we need to set the green one as 1. And here we have a green color. But okay, what I want is, like, in order to get something like this, look at how our rectangle is so big. Look at how big our rectangle is. And look at how small their one is. Look at how small. We need to transform it. And this is done with the help of matrices. We need to use matrices, and that's what we will do. That's what we'll do. Yeah. And look at how when we resize the window, everything stays the same. This is because now we can finally, now I can finally show you the use of this function that we commented out. This function, every time we resize the window, we've set it to call our function this one, which just changes the viewport to the current width and height. And now when we run it, now when we resize, look at how it tries to fit everything inside. This is because now we're telling, each time we resize, we're telling OpenGL where it should draw. And this was actually the GL viewport as well. We're telling it to draw in the entire screen from the start. But when we resize, to also resize where it draws. You have to stand up. So, that was just a tangent from last time. We need, let me just set this microphone. Okay, now our goal is to have a movable rectangle, but before we can move it around, we need to make it smaller and actually pick a position for it, which will happen by having matrices, which will also use uniforms. Let me think, how should we achieve this? Yeah, let's create a matrix. But we need to include, where are the libraries? Where is it? Shader. Where are the libraries? Inside where? Yeah, rules. And I think, how did we, because in order to have matrices in OpenGL, we need to use a library. We need a library inside here, math. Okay, GLM. We need GLM. This is in order to use matrices. And why do we need matrices? We need them because they make it really easy to work with vertices and manipulate vertices. Because here, for example, in our vertex shader, we will change. When we want to move an object, because right now the triangle is really big, we want to make it smaller and move it around. In order to do that, we will not change these vertices. They will stay the same. What we will change is we will change the vertices inside the vertex shader. This is where we will make the changes. We will multiply here by a matrix. We will multiply by a matrix. this is the easiest way to make changes. So we need to create so here we will say math. We need to create an identity matrix, and we need to multiply it by a specific matrix for moving around objects, and then one for scaling. But I'm getting ahead of myself. Let's create an identity matrix. This is our transformation matrix. Now we've created an identity matrix. Each array, each vector that we multiply by this identity matrix, the vector will stay the same. This does nothing. And actually, yeah, let's keep it like that. And let's scale it down. Let's scale it down, which is achieved by just multiplying it with another matrix. And this one is specifically for just scaling down or up. So we will scale down by 0.5. 0.5. So we will make it smaller. And that's it. That's our matrix. We need to use it inside the shader. Inside the vertex shader, here, we will have a uniform. I'll get into what uniforms are. And what should be the type. I forgot in OpenGl what the type should be. Like it's a matrix. Like, is it matrix 4? Like, was it like that? I have to check. Inside resources, my past fragment, my past vertex shader. Okay, mat4, yeah. And we just multiply it. And it's the transformation. The transformation matrix. And now, if we run it, our rectangle is gone because this matrix, this transformation matrix, it doesn't have any values. We haven't given it any value. And it uses some default ones, probably zeros, and it makes the rectangle disappear. And we don't want that. We want to use our matrix that we created here. In order to do that, we need to use our shader. In order to set our uniform, we have to first use the shader, and then we have to work with the uniform. But what exactly were the functions for that? Uniform get and set. It's actually is this. Okay. So here we can delete this and we can get this inside here. So here we get the location. So for our shader program and uniform name, the uniform name is our transformation matrix. And here we give it the value of our transformation matrix. And this should work. This should now scale down the rectangle. It's not scaling it down. Probably what we can try is we can do it in the render loop. Use. We can try doing it in the render loop. Still not working. It should be working even outside the render loop. Let's bring it down. What we're trying to do is trying to see why the shader program isn't reading our transformation matrix. So we're creating it. What else? We're multiplying it by the scaling matrix. We're using the shader program. We get the uniform location of our transformation. Oh, are there any errors? Oh, there are errors. Uniforms. Okay. And look at how this is because of our own code. Like these errors, we've coded these errors from. You can see here linking failed and vertex shader compilation error. This is why we wrote. That was the reason for writing these ones. Like here where we check for errors. Because if we didn't have them, we would be trying to, with a lot of debugging, trying to figure out that here instead of uniforms, it should be just uniform. And now when we run it, there's still an error. Too much data in type constructor. Ambiguous overloaded function reference. Vertex shader. I haven't seen this error. So matrix. Why is the position of vector 3? What? Let me delete these ones. Let me check my previous vertex shader. Yeah, it should be a vector 4. Yes. And transformation is a matrix 4. Yeah. This is 1 and this is 4, like we had it. That shouldn't be an issue. Oh, it worked. It worked. So now the rectangle is scaled down. The rectangle is scaled down, and now we can move it around, etc. But before we do that, currently the coordinates we're working with are between -1 and 1. And that's really difficult to work with, as we saw in the last stream when we tried to create the breakout game. Here, like, but do we actually, yeah, in order to use bigger coordinates, like instead of -1 to 1, if we want bigger coordinates, like from 0 to 800, which should be the width, or from 0 to 800, the height, and from 0 to 1200. In order to use big coordinates like that, instead of from 0, 1 to 1, we need another matrix. I think it's orthogonal matrix, which we can yoink from their breakout game. We can yoink it from in practice to the game. Where was it? Levels? Rendering? Projection? Yeah, this one. And here we let's just now if we use the identity matrix, it should be the same as before here. And now, because I want to focus just on the projection matrix, see what it does. Here we can, this is our projection matrix, which should just map values from, like, let's even remove this callback for when window size changes. I don't want it. Here we have size, the width is 1200, so here it should be 1200 by 900. So here it should be, I think this 1200 and this 900. So what this projection matrix should do is when we give it values, when we give it a value of 1200 and on the x-axis and 0 on the y-axis, it should give us something on the bottom of the screen. If we type 0, 0, 0 on the x and 0 on the y, it should be top left of the screen. Like this, because it will transform big coordinates to the smaller ones between -1 and 1. That's all it does. But we've just created it. We need to use it. And to use it, once again, we go into the vertex shader. And these uniforms, like, this is a way for us to give information to the shaders. The difference between what we did before with locations and uniforms is that uniforms can be even used directly in the fragment shader. They're global. Whereas in the fragment shader, we couldn't input values as we did before with locations. That's the main difference. And uniforms, we can have a lot of them. Here it should be projection matrix, and here we multiply by it as well. And now we need to set it. And we set it the same way as on the transformation matrix, which is here, projection. We can check. We can change this to projection. And here, projection. Now the values that we inputted, the small values, should give us actually a small rectangle. It's probably even too small. Let's scale it up and see. We're either making a big mistake or everything is working correctly. We will check from by scaling it up by 10. By 10. By 10. 10. 10. And let's start. Do you see it? It's this small rectangle there. We need to make it bigger here. We can make it actually, yeah, here now now the coordinates change a bit. We don't have a negative coordinate because we are multiplying by a projection matrix. We don't have a negative coordinate. We need to, it starts from 0, 0. Like now, before 0, 0 was in the center of the screen. It was in the center. Now 0, 0 is on top left. And 1200 by 900 is bottom right, just because of the projection matrix. So here we need to change our vertices. So now let's, so when it's negative, we'll have it just as 0, and positive will be a 1 for now. And here 1, here 1, here it will be 0, here 1, this is 0, 0, 0, 1, 0. Oh no. Yeah. This is 0. And this is 0. This should make a change. Let's scale it up even more, because we are doing something wrong. Let's scale it up by, I don't know, 100. By 100. Now it's a bit bigger, and it's only the bottom triangle. Let's, like, this should be upwards left, then this should be upwards right, then this should be down right. This should be bottom left. No, this should be top. This should be top. Oh, come on, what did I do? This should be top left. This should be bottom right. And this should be bottom left. Okay, now it should work. Okay, now we have a rectangle. And let's make it bigger here. Let's make it bigger here, so we don't have to scale it by so much. Ooh. here we scale it by, let's say, 10. I just don't want us to have to scale it so much. It's good enough. It's good enough. Yeah, no drop frames. The stream is perfect. Now, let's move it in the center of the screen. Let's move it by using inside math and using a transformation matrix. Rotate, rotate, scale. Where is translate? Let's translate it. Now, we have an issue, a possible issue, because the order matters. The order matters. Let's multiply by a translation matrix. This is just so we can move it. The issue is that here it's important we don't, it's important we do not mess up the order, because I think the order is we first have to scale it, then rotate it, and then we can move it. Movement, I think, was the last thing we can do. We want to move it in the center of the screen, so let's move it by so on the x-axis let's do 600, and on the y-axis let's do 450, and on the z it's 0 always. And let's run it. And here it's not on the center because the local origin is the top left, and we need to move it upwards and to the left by its half width and half height, but it's close enough. Let's just focus on moving it. We can center it. Okay, we can center it. I want it to be centered. So we have to move it upwards. So here minus 50 F, and here minus 50 F. This is, and here it's on the center. You know what? Let's have it here. Let's have it to be just once, and we will scale it. Yeah, let's have it as once, because it's easier to see its size like that. And here for the scaling, it was 100. It was 100. Because here when we move it to the left by 50 and up and upwards by 50 pixels, before here it was size of 10, like when we scale it upwards, but it's actually 100. Here the vertices were between 0 and 10. Now as between 0 and 1, the scaling is the actual size. It should be the same thing. Yeah, it's the same thing as before. Let's make it movable. Man, this is so much work. Let's make it movable. But I also need to eat. We'll make it movable by using the process input. Okay. Let's, because only place we can target movement is through process input. You know what? We can start music. Is it too loud? It should be around 40. Yeah, it's all right. Let's. Also, let me pour some water and we will move on. Next. Now here in process input, is the only place we can target pressed keys. So here when you press escape, it closes just because of this here. And here we have to actually move the player. Let me move up. Let me move up. Now, here we want when we press upwards or downwards or left and right, we have to target it here. And we also need to save this information somewhere. So we can have we can have for example some global variables like float, player x, which should start. It's not at I'm wondering. Yeah, I have to change it. And player y, which is not exactly this. It should be you know what? We can have player size as well. Player speed. Yeah, let's have player speed. It should be, I think, velocity. And here it should be actually let's because I want here to be like player x is this coordinate minus its size, player size divided by 2. And I'm wondering if it will work like that. Player size divided by 2. And let's go down to, where was it? Here, and for the scaling, here it should be player size. Player size. Player size. And let me move a window. Okay. here it should be player X, and here it should be player Y. Now it should be the same as before. Now it should be the same. Build failed. It's probably because, yeah, player size, it should be the first thing. Player size 100 F, and now we remove it from here, delete till this. Okay, now probably should work. Okay, it works like before, and now we can actually move it around. Before we can move it around, we need to do this math calculation inside the render loop. The easiest way to show why is if we leave it like that, and let's just break it and play around, and it will be the easiest to see what's up. So if we here, if it's the, I'll do it as the home row keys. So if it's the H key, if the H key is pressed, we should move left. So here we will change the player X minus player speed. Right. And player speed shouldn't be that much. It should move by, let's say, 10. This is to the left. Now to the right should be, I'll make it the L key is to the right, which should increase it, and move down should be player Y. To move downwards, like up, to move up, we need to remove. To move downwards, we need to add. So yeah, it's plus player speed. And to move upwards, it's minus. Now, when we run it, we need to change this to be, so for downwards, it will be the J key, and for upwards, it will be the key, the K key. And now let's run it, but it will not move now. It will not move because the values are probably changing here, player X and Y, but the rectangle is not moving because we are changing the matrix only once. We need to change it more times. So here we copy this, and here when we activate the shader, player movement, draw. So here in player movement, we do the same code. We do the same code, but I think we can do we can skip the projection matrix because we've already set it. And yeah, let's try like this and see what happens. Probably there is an error. Yo, yo, it's working. Yo, dude. Dude, it's working. We have a movable rectangle. Man, this was so much work. This was so much work. Oh, come on, man. I have to ban you. Ban. Sorry, dude. It works. And it took only 2 hours. It took only 2 hours. And this is all the code. How many lines? Let's see how many lines. So in 157 lines, we have this. In 157 lines. I'll be right back. Need to go to bathroom. I'm back. Man, we made so much progress. We rendered the triangle. We rendered the rectangle. We can move it around. Like, we made so much progress. Look at it. In our speedrunning application, we can move to spawning snake foot. We can move on to spawning snake foot. We can move to the next step. Yeah, we can move to next step. We don't have any drop frames. Man, this is such an improvement from last stream. We don't have any drop frames. And here. Now for dropping foods, let's go to the example. We're trying to spawn this red thing. we're trying to spawn the red thing, which is just drawing another rectangle. So we need another vertex array object. We need another vertex array object. And we need a random position. We need a random position. Let me think about it. How should we do it? How should we do it? Let's first, the first goal should be to just draw another rectangle and it to have the color red. That should be the first goal. So let's do it. Now, I think we can make this smaller, but let's leave it like that for now. What we're missing as well is delta time to multiply by delta time. Which we can do it. Like, what I like about coding from scratch is that you get an understanding of you get a lot deeper understanding of everything. So for delta time in Unity, I just knew about delta time and that's it. I didn't understand what exactly it means. But for here, you will see exactly what delta time is. I think it's... Oh, come on, man. I think it's like we get the current time. But how did we get the current time? It was with yeah, glfw get time. So a float current time and then previous time, and then we each time we, so delta time is we get the current time, previous time is from the previous frame, and we need to subtract them to get the delta, but let me see how exactly was it done. Where? It's inside rendering, but where exactly? Let's say collisions, ball. Process. I'm looking for delta time because currently when we move something, it's dependent on our frame rate. If we have a lot of frame rate, it makes it faster. But I'm trying to see, and we need delta time for that. And how exactly delta time? You know what? it's more interesting to try to make it on our own. Can we see what this gives? It gives a double. Okay. So previous time, let's just set it as 0, and here let's here set current time to get it, and here let's just initialize them as zeros. We get the current time, and when this is over, to say that previous time is current time, and here float delta time to be 0. Delta will be delta time will be current time minus previous time, and when we process input, here we will give delta time. We will give delta time here, float delta time, and now when we move something, it will be times the delta time. This will make frame rate, the movement frame rate independent, and hopefully it works. Like, I am doing it by memory. I am not using any reference for delta time. Let's see. Now the movement is quite slow. We can increase the movement speed. We can increase the speed to 50. It's still slow. Let's do it 100. It's still slow. 500. Now it's faster. We can leave it as at that. Hopefully we've implemented delta time properly. If not, it is what it is. Like, learning happens through making mistakes, so let's learn. Yeah, this is the current time minus previous time. That's it, yeah, we'll leave it as that. Now for spawning snake foot, let's render another rectangle. Here the issue is that we made it quite here we made it to be quite general, VO, VBO, but this is our player head, is the player head. So we need to rename it because we need to make room for the player foot, for the snake foot. So here, instead of vertices, it should be this is the rectangle of the, so player rectangle or player head vertices, and here it should be player VO and this should be player VBO. And now we can create the player foot, the snake foot. Snake foot vertices, and here snake foot vertices, snake foot vertices. And for this it's snake foot VO. And this is snake foot VBO. And this is snake foot VBO. And yeah, everything else it's the same. Everything else is the same. What else? The color. We need to change the color to red. So here these two ones and these two zeros, and we need to draw it. So here where we bind the player, we also need to bind, like here we bind the player VO and unbind it, and here we bind the vertex array. I was thinking, should we just join how's the progress on the game? I will start it in 1 second. Let's just render the snake foot VO and let's start. You can see the progress on the top right. This that they use for speedrunning. We're on the spawn snake foot. And here we have the snake foot, but we also we have a moving rectangle. This should be the player and it should be I think color green, and this red color rectangle should be the foot that doesn't move. Let me check. We have to see where is the problem. Where is the problem? We have the player VO, player VBO, we unbind it. Then you have the snake foot. We bind vertex array. Where's the mistake? Where's the mistake? What are we missing? I think we can try to unbind the VBO as well. Bind buffer. Let me check in blockage how I've done it before. Do I only unbind the V vertex array object? Yeah, I only unbind the vertex array object. Let's see what actually happens. So this red rectangle should be the player foot. Like we're trying to where is this? We're trying to make this. So this red dot should be the player foot and the green one should be the player head. We had the player head. Oh, you know what? Let's see here. So player rectangle vertices is the color green. Here are the color values. This is red, green and blue. We're setting the player head to be green, but for some reason, oh, I see. We need to change the matrix as well, because they're both on top of each other. That's what's happening. That's what's happening. We need, this is for player movement, but we also need, oh, okay, we need, oh, this became complicated. This became complicated because, chat, we are doing it all in one file. And I think we need some abstractions. Because here we are changing the matrix. Oh my. Here we are setting the transformation matrix for the player, but we're also changing it for the snake foot as well. So what we have to do is copy it, paste it, and here to don't scale it and don't translate it. Oh, no, we need to scale it to be the same size as the player. And for translating, we'll leave it at the center of the screen. No, we need to set the same kind of translation. We will copy the initial one. Like, now I need to... I think we need to make some abstractions. I think we need some abstractions. I think we need some abstractions. Here, player X, it should be this, and player Y should be half the screen, but like this. Like this. And now when we start it, here it works. We have the snake foot. And it's on top of the player. We have the snake foot and we have the player moving around. We need to... I think we need to abstract it, because when we eat the snake, because for two rectangles, it's not that much code. But when we need to spawn, when we eat the food, our player should grow. Our player should grow. Our player should grow. So, like this. Our player should grow. And each rectangle, for each one, we have to... And it's even impossible to do it manually. It has to be automated in some way. We need to abstract it. We can create... how can we abstract it? We can create a draw rectangle as functions, or we can create a class. Or we could create a class. How they do it, how it's done here, where they create the breakout game as an example, they use game object as an abstraction. So the ball is a game object, the paddle is a game object, each block is a game object. That's one possible abstraction we can do. That's one possible abstraction. How can we do this? That's one possible abstraction. Because when we edit, okay, we can check for collision. Like, we can randomly spawn the player foot. We can randomly spawn the player foot and we can check for collision. We can check for collision and we can destroy it once they're collided. But even destroying it, like, it has to have data on its own. It has to have data on its own. So we need a class. We need a class because it needs to. It will make it a lot easier to keep track of it. We also, for when we create, we can have a vector of game objects for the player that spawn all the rectangles behind it. But there's another issue. Look at how my player is gliding, which is an issue because I think it has to like move. It doesn't have to. It has to move like as it's here. When I press up, it should be like here. Pressing up should be here. That's how the snake game works. And we're currently checking if we're currently pressing the key. What we should rather check is if we have just pressed it once. And this should move it. Actually, it's different than that. The snake game actually has the rectangle moving like here, then here, then here. And if we press a direction, it just changes the direction. So if we press right, it starts moving to the right. So how can we do this? So it's like each second. This automatic movement, we can simplify it and not have it. And we can just check. Okay, you know what? What we can do is we can go here and here on, instead of press, we can check on release. Does it have something like this? Yeah, release. GFW release. Yank word. Paste. Paste. Delete. 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 Now what this will do, it doesn't let us to hold the key. Now we cannot is there an error? It crashed, I think. What? It's not starting. Why? Why is it not starting? It started instantly and it crashed. Just because of this. Oh, I see. I'm also doing it for the escape key. Let's have it as GLFW. It's closing the game. Let's have it as this. No, it's the same thing. It's the same thing. Sadly. How can we make it? GLFW. We have to look at GLFW on key release. We need on release. Key input. Yeah, but they use a special callback. They use a special callback. Input mode. Release. The action is one of press, repeat, or release. Emitted for every key press. How many keys? Intended for text input. Okay. If we use the callback, like if we use this function, need to sit down. If we use that function, if we use that function, we lose our control of the player, because we also give the player the delta time. We also give the delta time. I'm not sure, because here right now, here we use our own function and give it the delta time. But if we use their function, like to have it just as a callback, we have to change our process input to be like this. So we cannot give here the delta time, which is the proper way to do it, because the logic shouldn't be handled here. It should be handled at a different place. It should be abstracted. Like here, the only thing that should happen is to tell the game that certain key has been pressed, and to handle that pressing elsewhere. But I've just wanted to have it simple. I'm not sure how to handle when the player eats the food, when the snake eats the food, what happens with the with these things, how they spawn and how they move. Because look at how here, how it's moving like this. But my movement is like upwards. Like I can move a little bit and a little bit to the right. And when we create another object behind it, it will be something like this really weird one. But here, it's moving with the player width and height. We need to change the movement. Our movement is smooth. We need to make it rigid and to hop in a way. And we can increase the player speed to change this to every time pressing, like moving once will move it a lot, like the player width and height. but the problem is we can hold the button and it continues to move. I cannot figure out how to make it so it's limited only on, for example, key release. But when I do key release, it's also like this. I have no idea how we should tackle this. Let's... Only way to make this work is when we process the input. We should change how we process the input. The issue is that, okay, let's focus on moving to the right. And here, instead of GLFW press, let's make it release. I want when the player holds down the right, moving to the right, the player to move only once. Oh my god. I'm not pressing anything and it's currently in GLFW release. Weird. It's currently in GLFW release. What we can do is... we can create some kind of a lock. We can create some kind of a lock. Like when we're currently pressing to start the lock, and one like a boolean, to set a boolean, and when we release a key, the boolean is false, and we can change the location once more. I'm thinking of I'm trying to think of a naive solution. If we don't solve this, like we cannot move, we cannot finish the game if we don't solve this. We cannot move forward. What we can do is... I'm not sure. You know what? Let's do it as else ifs. Else if here like this and this and here else if like this. And last else if that's it. And can we make it prettier? Now I want and here if it's else we'll do it like this. Boolean lock movement false, and here if lock movement, if movement is locked, we return even though we're continuing to press. And here we lock movement equals true, and here on else lock movement is false, and we repeat. This is the naive solution I came up with. Our goal is not to write perfect code. Our goal is to struggle. Our goal is to struggle because when you struggle with something, the next time you read a book or read upon it, the next time you read about this or how to do it properly, you will pay much more attention, because before you struggled on this and you wrote extremely bad code. This is the fastest way to learn. Let's see if this worked. Now it worked. Now if I hold the right key, it's not moving. It moves only once. It works. It's a naive solution. It's probably not the right way to do it, but it works. And I struggled. So when I see the proper solution, I will for sure remember it. So now for player speed, we can change it to be you know what? We can ignore delta time. We don't need delta time. Here, we can ignore it. We can for sure ignore it because we are just moving one step at a time. We're moving one step at a time. And now it should be, and now we can change player speed to be its size. Player size. Now pressing the key once should move it its size. And here. Yo! It's probably really ugly code. It's probably the wrong way, but it's working. Yo. It's working. And now we can move forward. Dude. We can move forward. What else? What else? Now we spawn the snake food. Let's spawn it at a random position. We can abstract away the creation of a rectangle. We can abstract it because it will make it easier to set a random position for the rectangle. We can create a class, I think. We can create a class that is we can create a class that is for rendering and keeping relative values for a rectangle. Yeah, we can abstract it away. Yeah, let's create a class. Let's create a class, but first let me go in my git ignore and I want to make a commit. Main cpp, so we will call it player movement. And we push. Now we need to abstract it, so we can create a class. Class rectangle object, and it will have public no, square. It's a square, and it will have x, y. It will have a size. We initialize it. We initialize those values, and we need unsigned int for the VO only. The VBO, we don't need to keep track of it. Actually, for the VO, we don't even need to keep track of the VO. Yeah. We don't need to keep track of the VO. So we need to init it, initialize it, and but it should be like a void. It should be a void function. Yeah, init. And we need a void function of draw. Yeah. We need to initialize it. Our goal right now is to have the same functionality as before, but through our abstraction. So we take away this. Yeah, I was thinking here we set the color for each vertex, but it's the same color, so we can store it in a uniform. We don't need to pass it like this. Let's just move it to here where we initialize, and here we change. I think we need to store the VO. We'll just not we'll just not access it. VO. We delete this, and here VO, VO, and here is just a regular VBO. VBO, the VBO. Here size of, and here the vertices, and here vertices. Vertices. What else? We will ignore the color. We ignore the color. We need to change the size. We need to change the size, the stride to be 2. Okay. And here we need to delete all of this. To have, we'll just store the positions. Need to stand up. Now, this is just for initialization. This is just for initialization. Next. And now for drawing, we want color as well, but I'll be right back. I need to go bathroom. I'm back. Now, let's we want, I want to store the color, but as GLM vector3 color. Yeah. And here we will complete square. Yeah, it looks all right. So now we initialize it. We have the VO generated, and we need to draw it. So for drawing, we also need unsigned int shader program. We need to pass a shader program, and for drawing we need to work with the transformation matrix here, and we need to draw. So we generate the transformation matrix, which is translation, player X and player Y, and player side. Okay, here it's just X, here Y. We can even have it as here to be. Let's keep it as X and Y. I was thinking of making it a vector of size 2, but let's keep it like that. What else? We set the transformation matrix. What about the size? Yeah, it's called just size. So here it's size, and here shader program. And now for drawing, we bind the VO. We draw 6 vertices and we unbind it. I think that's okay. And we also want to set the color. The color, because we don't need to set it for every vertex, it will be a uniform color instead of an in. We delete this, and this. Here color, yeah, once again just color, but we'll do it we will do it here. We get the color uniform and we set it to yeah, but can we do it like that? Like we can say like here color, but oh no. Geo uniform, yeah, let's search on the internet on documentation and to see how to set up float. Yeah, geo uniform 3f. We need geo uniform 3f. Yeah, that's it. Yeah, we set the color. And here we ignore this. And here we how should we do this? Now we, as the player is a class, square class, we don't have this player X, player Y. We could have it here. We could have it here as reference to square player, and just to change here player X, and here player X, and here player Y, player Y. Okay. And player speed, Yeah, player speed will be separate variable. Float player speed equals, and we'll keep it, but it will be, you know what, let's call it, let's just create it here. Let's create it here to be speed, and here it will be this speed will be the size. It will be equal to the size. It will be equal to the size, and what else? Yeah, okay. And so here it will be player speed. Player speed. Player speed. Player speed. And we need to pass it along. Process input. Here it should be the player, but we haven't created the player. We have to sit down. We haven't created the player. We'll create the player. For now, we'll remove the player foot, like the red square. We'll remove the red square and have just the green one for now. Once we have the green one through our abstraction, we will add back the player foot and we'll make the foot spawn randomly. What we can also do is here in the constructor we can also call the init function. We can call the init function. Now we will remove even the snake foot. We'll remove it. We'll just initialize the transformation matrix as the identity one and set it. And we'll create here the player. So square player. Oh, come on. Square player. And it's the, well, red, green, blue. No, it should be red, green. It should be green color. 450 size. I think it should be 100 size. 100 size. Yeah, we have the player. And let's render the player. We don't need all of this. Here we say player draw. And we need to give the shader program. Look at how simplified it is. And look, we have the player and we've abstracted it away. Now look how simple and easy it will be to add the foot. Snake foot. It will start in the same X and Y, same size, but it will be the red color. And we draw it. Look at how snake foot draw. Look at how simple it is. And here is the snake foot. Everything is working perfectly. And now the cool thing is that we can draw easily multiple rectangles. So we can easily have the functionality of eating the rectangle. So we need to figure out how to spawn the food randomly. We need to see how to spawn it randomly. How can we spawn it randomly? So we need a random float value, like we have. We should change it because, like, look at how my head can be like this here. I want it to be like to the edge, perfectly to the edge. So what we can do is change the player X location to be, let's start it in the 0x location and 0y, and let's check it out. And here it's perfect. It's perfect. And on the y axis, how is it? It's perfect on the y. Now the issue is that the foot is not aligned. We can, and how to make it actually. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So to spawn the foot randomly, we have 12 on the x-axis options. So 12 on the x-axis, and how much on the y-axis can we spawn? How many options do we have on the y-axis? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 options on the y-axis. So we need to generate integer from 1 to 12 and from 1 to 9. And based on that, we create a rectangle there. Yeah, so we'll create a function. We'll create a function that takes, okay, let's make the function. Where will we put it? It will return a square, spawn snake foot, and it will get int x and int y. And it will return a square that is x times so it's 12. Yeah, and the color should be red. And here, for example, we say create our square snake foot is spawn snake foot at, for example, 0, 0. Let's spawn it at 0, 0. And here it's at 0, 0. So now let's do it. Bottom right. So it should be 11, 8. Because since it starts from 0, it's 0 to 11. And here 0 to 8. And let's start it. Now it should be on the bottom right. Yeah, now it's on bottom right. Perfect. Now we need to generate random values between these ones. And so let's look at C++ generate random integer. How to generate random int? Random. Isn't there some simple way to generate a random number in C++? This is between 0 and 9. Perfect. Perfect. So let's random x location and random y location, and let's have it. This is between this should make it between 0 and 9. So this should be 12 and this should be 9. So this will be between 0 and 8. And here we say random x, random y, and then we start, and here is bounded here randomly. Now if we start again, it's bounded again here, because our randomness is always the same. We need to do this, provide a seed, so it's not the same every time. Is it like this? Okay, now it's different. Now it's here and we can reach it. Now it's down here. And now it's here. Okay. We can spawn the snake food. Now we have to eat the snake food. To eat the snake food, we don't have to even check for collision. We can store the current snake food x and y and check if our x and y is the same. Because they should be matching. If we have, because of the way our game works, we don't need complex collision detections. Man, 3 hours in, we are getting closer. We need to spawn snake food. Can we make it? Can we make spawn snake food random, and here delete this, and here to have this 12, 9, and now here we delete this, and here we spawn snake food random, and it should be the same thing. Yeah, it's the same thing. Now, for eating the snake food, we want to spawn it once more. So when we move the player, we can do it like this is current snake food, and we can do it like current snake food, and we can pass it to our input. We can pass it to our process input here, player and current snake food, and we can here do square reference current snake food. So now when we move the player, after movement, if player position equals current snake food, we respawn it. Will it work like that? Yo! Yo! Look! Yo! Yo! It's working! Dude! Oh my god! Dude! Yo! Yo! It's working! Man, this took about 3 hours. Yo! And all of this is in a single file, using from scratch, using OpenGl and GLFW. Yo! Can I change the latency of the stream settings? Can I make it? No, it's before we start. Okay. Yo, dude. Yo. Yes. Now we're on the next phase. Snake grows on eating food. Now we want our snake to... Where is it? We want our snake here to grow. How can we achieve this? Now I'm not sure. How can we do this? Okay. We move the player head. We can move it. We can eat the red rectangle. We can eat the red rectangle. Once we eat it, we want to spawn rectangle behind our current one. Oh, you know what? Our player, we can create another class that is the player and is a vector of rectangles. And each rectangle has its own position. When we move the head, it will pass its position to all the previous rectangles, and they will have the new position. That's how we will do it. And the length of the vector will be just depending on how many foods we have eaten. So for debug purposes, let's just change the length of the snake no matter how much we have eaten. let's create another class snake that is vector of square. I think it was like this, and here std. I think we need to include it. Yeah, snake, and and all of them, yeah. And let's, in our constructor, will push back square. Okay, we need a position as well. Float x and float y. This is our starting points, and here let me move up. And here it will be all of the squares will spawn. Okay, and I also want here to have length. So int length, and by default it's 1. So for this we push back here. But watch, yeah, we push back them. Where's there a mistake? Where's there a mistake here? Expected. Like this? Yeah. So we will spawn all of the rectangles in the same position. So here it should be the X, and here the Y. And they will be all the same size. And the same color, same position. We spawn them, and for drawing, void draw, we need to have a shader program. Unsigned int shader program, and we draw all of them. Now now for the movement. For the movement, we want, when we press right to move right, we move the head to the right, and all of the other ones, before we move the head to the right, we will move all the other ones to have the same position. Like, let me think about it. And where exactly is the head? I think when we access the zero position, I think the last element is the head actually. And the tail is the 0th position. So we can go through from 0 to the last one. So the 0th position will be the same position. So the 0th element, so the tail, will have the same position as the next element. And doing this up until we reach the head, which doesn't have anything after it. It will be the last element. When we reach the last element, we actually move it in the direction that we decided should be moved. Yeah, perfect. Okay, chat, we may be able to do it in one stream. We may be able to do it. We may be able to do it. What should we do? So we have the rendering, we have the initialization, we want movement. Okay, so okay, let's create a void move float x and float y, and we go through all of the elements. Yeah, so the current one is so zeroed. Oh, this one starts from the other way around. Oh, this works as well. Yeah, this works as well. It's the same idea as my own, but VS Code suggested doing it backwards, which works as well. We also want yeah, let's leave it as that, and let's go here where we have the player. It will be snake. Yeah, let's leave it as player, and here we remove all of this, but for length let's have it as 5. And here, why is it giving an issue? Float x, float y. Oh, we need to make it public. We need to make it public. Our snake, we need to make them public. And do we have the snake? Yes, we have the snake. And now here on process input, we receive a snake, and we I need to turn off my AC. Okay, let's start moving them. So player move, and it's player x. No, we are not. What? We need to store. We need to keep track of its current x and y. So float x, y. That's it. And here, this x equals x, and this y equals y. And here, when we move it, we or we could actually get the position. How to move it, because when we're saying move to the x and y, we need to know where it was before that. Or it's like move. You know what? Let's have the movement as delta, x delta and y delta, and here it's like plus equals x delta and y delta. This is just the change, and here we don't need this and this. So now in our movement, in our process of movement, we move to the x. So here delta y is 0 and x is minus, but we need the speed as well. I'll be right back. Need to go to bathroom. I'm back. So now, okay. Need to be down. Let's finish this game. Now we are targeting. We are trying to make the snake grow. We are trying to make the snake grow. We're trying to make the snake grow. So here, let me bring my chat. Here, we're moving it. Okay, the speed. The speed. Yeah, we need to set up the speed as well. So here we want float speed. Here float speed, and here speed. That's it. No, we want this speed to equal speed. Yeah. And so now in process input. Yeah, in process input here, when we move to the left, we the change in the x direction is minus player speed. And here, yeah. And here it's plus player speed. Here it's the change in the X is 0. And for the Y, move down, it's positive. And here it's negative. Now it should work. Now it should work. What's the issue? X is not member of snake. Here we should check player snake the... Oh my god. We need to be able to get the current position, the head position. So let's go to snake and we want get head position, which is the head the 0th one, because we will push, and when we push it pushes to the back. Okay, the head is the 0th position, right? And now processing input GLM vec2 head position, and here we check for head position, and here head position. Now it should be ready for action. Oh my god, it's not working. We have a little square up here, so the transformation matrix is not working. Why? It's moving. Oh, it's probably moving all of the... Okay, maybe something with the draw. Player draw. Player draw. So for the snake, we go through each one of them and we draw each one of them. And the side... No, here... we're making a mistake. This is the size, it shouldn't be the speed. But it's the same thing for us. It's the same thing. Oh, we're not setting it. Probably. So where is our player? Here, player. Why do we have a 5 here? Oh, okay. 100. 100. Yo! Dude! Yo! What? What? Yo! I didn't expect this at all, man. I didn't expect it at all to work like this. Yo! Dude. Shouldn't there be space? You know what? I can make... Yeah, let's keep it. I was thinking of making... I was thinking of adding spaces here, so each rectangle is more visible, but it will make it too complicated. Like, it's enough as it is right now. Now, when we need to add for the snake, we need to make it to add a function increase size. Increase size. Increase size. What's this? Okay, we create another square. We push it back with the red, green, blue. Okay, same color, same speed. X and Y, we push it back. And what else? Let's change this to size. Size, just so it's not confusing. Size, and here size, and for here where we move it by speed, it's actually the size. Size, and now here we want to respawn the player foot and to player increase size. We need to increase player size, and let's start the player as one block. Let's start the player as one block. Where's the player? Here. Let's start it as one block. And now let's... there's an error somewhere. Here. Size. And now when we eat a block, it should increase the size of the snake. Yo, it's working. Now it's 3. Now it should be 4. Now it's 4. Now it's 5. Now it's bigger. Bigger. Dude. Honestly, I didn't expect we will get this far. I didn't expect we will get this far. We're closing on 4 hours. Okay. Now, snake rolls on eating food. Snake food respawns different positions. Now we need to add game over. We need to add game over. Game over happens if we eat ourselves. If the head is same position as one of its other blocks. So game over we cannot boolean check collision, which should be head position, if we go through each of the other rectangles and check if the current head position equals to one of them. If yes, return true. If not, return false. Okay, perfect. Visual Studio Code is reading my mind. Now let's we want on movement if player check collision, we game over. Okay, now let's grow our snake up. Oh, output. Did we get a game over here? We don't get this because the terminal closes. I wonder how we can output stuff. But check collision. Check collision. The problem here is that when we eat a food, our next body part spawns at the same position as our head. Spawns at the same position as our head, and we then check collision. We should check collision. You know what? Let's remove this and let's go in our move, and the moment we move our head, that's when we check collision. If come on. If check collision, no, we cannot close the window from here. Checking collision. It should be after we have moved. Oh, we increase size here. Okay. We should do it like this here. Okay, now it should work. And now, oh come on. It didn't work again. We move the player, and after we've moved the player, we check collision. Alright? After we move it. After we move it, where do we increase size? So we move it, we eat the snake food, it increases, like we move it. We check for collisions, no collisions. We are at the snake food, we increase size. We press a button, move it, and after moving, we check for collision. So there shouldn't be an issue. Let me check. Let me check the code. So the movement goes through each one and changes the position. And changes the head. And check collision. Check collision goes through each one and sees if it's the same as the head. And we start from, we ignore the head for sure. What are we missing? And get head position just gets the position of the head. So what's the issue? It shouldn't be. The only time it messes up is when we eat the food. Okay, we managed to eat the food. Need to stand up. We managed to eat the food. What's the issue? What? Okay, so... Oh, successfully connected. We have trouble connecting to Twitch, but I think we are live on YouTube. Yeah. Oh, come on. For some reason, we lost connection. Okay. We can just continue streaming on YouTube. Can continue streaming on YouTube. Yeah. So, what we currently have, let's bring back the music. Right now, we can move around the head. And when we eat the food, it's game over, sadly, because it's colliding with its tail, because it spawns the tail on top of its head. That's the current issue right now. Yeah. No way we'll be able to connect back to Twitch. Okay. Let's check. Why does it think it's colliding with the head? Let's check collision. Okay. process input. We move the player after we... Oh, you know what? I see. Because this function gets called again and again, even if we don't press anything. Even if we don't press anything, this function gets called again and again. All right. Yeah, so what we will do is we are checking collision too many times. We need to check it only upon movement. So you know what? When we move it, we'll return a bool. We return check collision. We return check collision. And so now we set it as bool collision false, and here after movement it's collision equals like this, and here like this, here like this, and here if collision. Okay, now it should work. Now it should work. Now it should work. Now, okay, it works. Now if we collide with our body part, like this, okay, it's game over. It's game over once we collide with one of our body parts. What we can also do is to constantly have it move around, but to constantly have it move around, oh, I think Twitch should be somehow Twitch shows its live. Weird. I want the snake to move around on its own, and this to be every second. And what we decide is the direction, but I think we're complicating things if we do it like this. We can check if 1 second has passed, and if so, to move the snake in the default direction, and we change the direction by... We can try. You know what? YOLO. We can try. We're about 4 hours in. We can try. We can try. So here we can pass delta time. We can pass delta time. Delta time. And how much does it return? in seconds. Okay, in seconds. And we can... I'm just doing a naive approach. It may be the wrong way, but we want to reach our goal, struggle, and with the struggle is how we learn. The next time we read the proper way, we'll have more attention to the proper way once we've struggled in the wrong way. So here we do... we want delta time. So float delta time. And let's store in a global float past time equals 0. Let me... past time is 0. Past time is 0. So now every time we process input, we and let's have direction for the snake. Snake yeah, so our velocity. So let's set it as GLM vector to direction. Yeah, direction. And let's have it set as a default one, as 0.0, no, as no, when we initialize it. When we initialize it, the direction will be on the to the right. So the x should be size, so we increase it, and the y will be 0. Yeah, that will be the direction, and movement will be just it will take nothing. It will be here, it will be the direction x, direction y, but why is it is undefined direction. Okay, and void set direction, and here we set the direction. Fine. And now in our process input we will move it every second. So we in past time we add the delta time. If past time is more than a second, we player move. So we also need to check the collision. Collision equals player move. Right? And we also past time we set it as 0, or actually we set it, we just subtract the 1. We subtract 1, and for moving left we are just changing the direction. Set direction, and this move right is just the positive. Move down should be just change direction. Here it's 0. And this is move down, we increase it. And here we subtract. And this should be it. And hopefully this works. Yo! I'm currently not pressing it, okay? I'm currently not pressing it. And it's moving on its own. Yo! 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 It's currently moving on its own. And let's make check collision. Where is check collision? I also want the head to not be outside of the bounds. So if head position, yeah, if it's outside of the bounds, it should also fail. So if I move it to the left and it's outside, it's game over. Okay. So now let's track the score. We track the score by having a global variable int score equals 0. And let's say when we collide, so where's player move, where's process input? Where is process input? Process input, and when there's collision, when we eat a food, we score plus equals 1. And if score equals 10, it's you win. You won. And that's it. Can we log this? glfw log. Can we? Because when we output, sadly it's not in the window. We can leave it as this. So now let's try to reach 5, or yeah, let's reach score of 10. Let's reach score of 10. Let's reach score of 10. Score of 10, now it's 1. And now it's 2. Now it's 3, 4, 5, 6, 7, 8. I'm just changing the song. 9. And now it's somewhere below me. Oh, here it is. Oh, I pressed to the left. I pressed to the left and it was game over. But if I reach, let's change it to 5. Let's change it to 5 and let's make it every 0.5. Let's make it faster. Let's make it faster. One, 2, 3, 4. This should be the last one. 5, and it's we won. It's just there's no labels telling me you won. It's just see out to the terminal, but it closes instantly. But that's it. Chat, we made it. That's our game. We made it, chat. Our own game from scratch in one file. For 4 hours. It took us 4 hours and 268 lines of code. This is all of it. This is all of the code. We just have one class for rendering each square, and we have a class for the snake itself, which is just a vector of squares. And I'm really surprised that the snake class is very little code. Very little. And then we process input, where is most of our logic, and this should be separated, but you know. And here it was cool that we're processing if a second has passed through delta time, and we have our own vertex and fragment shader, and that's it. And that's the game. For 4 hours we managed to make a working game. Dude, this is awesome. You know what? Let's remove the limit. Let's make it a lot faster. Let's play around. Let's make it where's let's make it faster. But where was process input? Yeah, here. And let's make it 2 times faster. And let's make the win be... Let's win the game after a score of 50, for example. And let's start now. Oh, fuck. It's a lot faster. This 1, 2, 3. Oh, come on. You know what? Let's actually make it more responsive by making this movement at the last step. After all of this. After all of this. And let's try again. Now it should be more responsive. Oh, come on. Oh, come on. Yo. Yo. Oh. This is in the way. Let's try again. Okay. I'm trying to get a high score here. Ah, okay, let's just leave it at that. Okay, thank you for watching. It was awesome stream.